chapter 20. So the enzyme here is a catalyst. The catalyst is consumed in the first step, but in the last step, it's regenerated. So here we have the catalyst, then it's reacting here, but then regenerated here, and then it can react again. And so the overall concentration of the catalyst doesn't change. And there are different ways that catalysts can work. In this case, it's weakening this bond, making the bond easier to break, requiring less energy to break it. This is a more complex kinetics here for smog. Smog, we can see that the species concentrations change. Like initially, you generate NO from emissions, and you have unburnt hydrocarbons. So this would be exhaust emissions from a car. Unburnt hydrocarbons and nitrogen monoxide or nitric oxide. But those react. The nitric oxide is quickly converted into nitrogen dioxide through oxidation with air. And we end up generating ozone and pan with time. Ozone is not very stable. Ozone, you might have a unimolecular collision. So for example, if ozone hits the wall, then that could break up into O2 and O. And in fact, that's what could happen. When ozone hits a wall or an inert molecule, you'll generate oxygen, which is stable, but you'll also generate atomic oxygen, which is unstable and very reactive. And that very reactive oxygen species will cause irritation. But let's look at some more catalyst here. And so carbon monoxide is another product of automobile exhaust or combustion, and nitric oxide. I'd said nitrogen and oxygen are very stable. They are. The air consists of nitrogen and oxygen. But if you subject nitrogen and oxygen to very high temperatures and very high pressures, then you can generate nitric oxide. And so these are two pollutants. And one of the catalysts they use is rhodium. They used to use platinum and palladium, which are very expensive metals, but they do pretty much the same thing. And they're looking for cheaper metals to use, not ones that are rare and expensive. But this is called a heterogeneous catalyst, in which we have gas phase and the rhodium solid. And it's thought that we need a metal here because the metals have empty d orbitals, and those empty d orbitals can act as active sites in which these molecules can bind to. And so the first step is adsorption of molecules onto the surface of the catalyst. This next step is reaction of those molecules. So there's going to be a reaction, and we form a product. When we form a product, we'll get desorption, because the electronic structure will change quite a bit. And so without a catalyst, the reaction is very slow because the activation energy is very high. But with a catalyst, it provides an alternate mechanism, an alternate pathway, a lower energy pathway. So what we have is an absorption, followed by reaction, surface reaction, they call it here, followed by desorption. So the surface reaction is going to be RDS, but when you look at the RDS for here compared to here, this is much faster. With the catalyst. There's a lot of research going in, what exactly is the mechanism, how are the electrons rearranged? And so it's not fully well developed, and so people are looking for new catalysts in different ways. One way is just trying out a whole bunch of different metals and metal alloys and see which one works the best. Other ways are trying to model it theoretically and seeing if they can figure out the optimum alloy or optimum metal to use. Same thought. Here's another type of homogeneous catalyst, like enzyme kinetics. Enzyme kinetics would be homogeneous. This is homogeneous too, and that is they're both in the same phase. So this is formic acid decomposition without catalyst. This is formic acid decomposition with catalyst. And you can see the activation energies are quite a bit smaller. And so let's take a closer look at this to see how this catalyst operates. So what they're showing is that formic acid decomposition without catalyst happens in this one hump here. And so let's take a look at how that might occur here. Normally when hydrogen's bonded to carbon, we don't think of it as being very acidic. But when I look at this molecule, there are two acidic hydrogens here. This one's pretty acidic. And normally we consider this one non-acidic, except for the carbon there. What's the oxidation state of the carbon here? Well, in a typical hydrocarbon, the carbons are electron rich. But in this particular case, this carbon's not electron rich. This carbon's electron poor. And what is the oxidation state of it? +2? Close. +3. So this is a +3 carbon. A +3 carbon is going to be much more electronegative than a 0 or negative carbon. It being much more electronegative, it's going to make this hydrogen much more polar than it normally is. Normally when we have a hydrogen-carbon bond, we call it a hydrocarbon bond. The hydrocarbon bonds are non-polar, except this one's polar. This one's polar because that carbon is electron poor. And so what this does is it makes this hydrogen more acidic than it normally is. This one's the most acidic hydrogen, and then this one would be fairly acidic. Compared to something like acetic acid. In acetic acid, the hydrogens there that are bonded to carbon are totally non-acidic. So what can happen is a vibration can occur. If we have a significant vibration, then this sp3 lone pair can get pushed into this S. And we have an s-sp3 sigma bond here. Those can get kicked out onto the carbon here. And so first, this oxygen attacks the hydrogen by the vibration here. Okay, when that hydrogen attaches to this oxygen, then it makes this oxygen positive. And since it's positive, it's going to pull off these electrons here to make water. And then we aren't going to have an octet here, so we're going to have to drop a lone pair. So they do this in one step. I'd rather do this in a few steps rather than all at once, regardless if it happens all at once or not. And so what we're going to end up with is this. We're going to end up with a carbon monoxide and the water. Yeah. So probably this is a slow step here. And that's going to require this activation energy here. What if we use an acid catalyst, though? And so this is the uncatalyzed reaction. If we use a catalyst in this reaction, then we can see that it's going to change the energetics of this quite a bit. So rather than this oxygen trying to pluck off this hydrogen from the carbon, if we have some acid readily available, H+, then there's no fight here. And this could easily just go ahead and pick up this. This is an empty s orbital. So we'll create an sp3s sigma bond here. And so what does that generate? It's going to generate this. I should have broken that one up into multiple steps as well. Yes. But we would have generated this over here. Because if this oxygen plucks off this hydrogen, then we're going to be left with an oxygen with 3 bonds and then 1 lone pair. This is an oxygen with 3 bonds and 1 lone pair. When we look at the formal charge of this, the formal charge is plus. So what's going to happen here is that these electrons are going to be pulled by the oxygen. So this tug of war will end up in something like that. And then we'll get this structure here. And water. Well, this HCl unit isn't so stable looking. Carbon doesn't have an octet, there's a formal charge. And so how can we rearrange the electrons here to further stabilize this? So one thing that could be done is this carbon's going to take the electrons from hydrogen here. But that still doesn't cure the octet problem. And so to fix the octet problem, we'll take a lone pair and convert that into bonding pair, like this. And so what we end up with is this structure here. Carbon monoxide, H+, and water. So again, the catalyst is consumed in the first step, but regenerated before the end of the reaction, or at the end of the reaction. Yeah. And so the catalyst helps the reaction, but it isn't consumed in the reaction. Well, it is consumed, but it is regenerated. So in that sense, it's not consumed in the reaction. Okay, so if you compare this, the energetics of this, oxygen taking this hydrogen versus the energetics of oxygen taking this hydrogen, this is going to be much lower energy, much easier to do. So the acid catalyzed decomposition should go much faster. So this would be the proposed mechanism for that. And so normally when we think about mechanisms, there's two things that we think about. One is we think about mechanisms in, like we did for the reactions, HI and ICl or H. And two, we think about mechanisms in the sense of rearranging electrons like this. Here, we aren't going to do the kinetics of this. This is just mechanistically how things happen. All right, that's the end of chapter 20. But to try to do a little bit more catch up, well, let's take a look at chapter 19, which is redox. The major application of redox is electrochemistry. And we have batteries, which are electrochemical cells that generate electricity, and then we have electrolytic cells. And so batteries use chemical potential and convert that into electrical energy. And electrolytic cells use electrical energy, or electrical work, to convert that into chemical potential energy. So let's look at batteries in a little bit more detail here. This is copper metal with silver nitrate. And so what's happening here is the silver ions are oxidizing the copper to precipitate or deposit silver crystals on the surface. And the copper metal atoms are losing electrons to form copper-2 ions. The copper-2 ions lead to the blue color here. Over here, there's no reaction. That's not going to generate electricity. What we have to do is we have to separate that into two beakers. Over here, we have our oxidizing agents, silver ions. Silver ions are going to try to oxidize silver. It's not going to be successful. So we call this an inert electrode. And so it's pulling on the electrons, and it's not going to take the electrons until it hits copper. Okay, when the silver ions pull the electrons, they can pull the electrons off copper, will generate copper 2. So we need 2 silver ions to take 2 electrons and generate copper 2. And so in this case, we can generate electricity, that is a flow of electrons through here. And there's going to be a voltage, a force on that, 0.46 volts. Yeah. In order for this to work, we need a salt bridge here. And so let's talk a little bit about the parts to this. All right, looking at the parts to this. Over here on the left, we have the anode. In the anode, this is where oxidation occurs. So we call this the oxidation half. Over here is the cathode. And at the cathode, we have reduction occur. So this would be the reduction half. When we oxidize something, we generate electrons. So here we're oxidizing copper. So the oxidation half reaction is copper solid goes to copper 2 plus 2 electrons. Over here, the reduction half, reduction is gain, oxidation is loss. And so we'll have silver ions plus an electron yields silver solid. The net reaction is going to be copper solid plus 2 silver ions yields copper 2 plus 2 silver solids. That would be the net reaction. So normally we write this in this way: the anode on the left followed by the cathode. So it goes alphabetical order, A, C. And the same thing, oxidation comes before reduction, so it's alphabetical as well. If we write it like this, then the electrons flow from left to right. So the direction of flow is this way. And when we look at the anode is where the anions migrate to. So for every copper 2 plus that's generated, we'll need 2 nitrates to neutralize that charge. And for every silver ion consumed, we'll need 1 potassium. So here, if we have 2 silver ions being consumed, we're going to need 2 potassiums to migrate towards the cathode. And so the cathode is where the cations go, the anode is where the anions go. Now, the cathode itself is made out of silver. And so this is called an inert electrode. It's an inert electrode because silver is not a reactant. In fact, silver is just a product. And so what's going to happen is the silver is going to deposit on silver. But we could use any other inert electrode like platinum. Platinum is a very common inert electrode, but we deposit silver on top of platinum, which isn't as clean. Over here, this electrode is a reactive electrode. And it's reactive because copper is a reducing agent. And so copper reacts to produce copper 2 plus and 2 electrons. So that's a reactive electrode. So this is the basics of the cell. And then we have the salt bridge. We can use whatever salt we want in the salt bridge. In this case, potassium nitrate. This is a shorthand way of representing a cell. This is called a cell diagram. So if I have this cell diagram, zinc solid goes to Zn 2 plus. aqueous 1 molar. Double bar, copper 2 plus, aqueous 1 molar, goes to copper solid. If I write it like this, then what I have is I have the anode on the left and then the cathode on the right. And so that follows convention. And so the cell diagram is a shorthand way of representing this cell. So I'll draw a schematic of this cell. And the schematic of this cell is zinc is going to be the anode. And it's a reactive anode because zinc solid actually reacts to form zinc ion plus 2 electrons. And those 2 electrons get fed over to the cathode. Okay, and so the zinc solid is going to generate Zn2 plus AQ here. And then 2 electrons are going to get fed into the circuit. And they're going to go over to the cathode. The cathode is going to be made out of copper, and it's going to be an inert electrode because it's being attacked by copper ions. So copper ions, excuse me, are not going to successfully oxidize the copper. However, these 2 electrons are going to travel from the anode to the cathode, and the cathode, the inert electrode here, is going to feed the electrons to the copper, which is going to deposit copper metal on the surface of the electrode here. And so the reaction over here is going to be copper 2 plus 2 electrons yields copper solid. So we can label this diagram here in the schematic. This is going to be the anode. Anode is where electrons are being generated. So anode is where oxidation occurs. Oxidation is going to generate the electrons, and the electrons are going to flow left to right. As long as I have a salt bridge in here, I'm missing that, so the salt bridge. In the salt bridge, the anions in the salt bridge travel to the anode, the cations in the salt bridge travel to the cathode. So this is oxidation. Over here at the cathode, we have reduction occur. And so the net reaction here is going to be Zn solid plus Cu2 plus yields Zn2 plus Cu solid. All right, to keep this under standard conditions, we use 1 molar concentration. So that means that the zinc has to be a 1 molar and the copper has to be a 1 molar. Over here, we put in a copper sulfate. So the sulfate would be a 1 molar too. The salt bridge will compensate for the lost copper cations and for the generation of zinc ions here.
What is the 18 for 1 molar?
Oh yeah, aqueous. I usually don't write that. In fact, I probably won't write it anymore. So, what this solid line represents is different phases. So solid phase, aqueous phase, so different phases. What the double line here means is salt bridge. And single line here are different phases, aqueous, solid. So let's go back to the previous cell here. If we look at the previous cell and measure the voltage comes out to 0.460 volts. 0.460 volts is involved in this tug of war. Now, silver ion is trying to take the electrons, but copper is resisting. You know, it's not so easy to oxidize copper, but silver ions can do it. And so this 0.46 volts is a composite of the pulling strength of copper and, you know, the fighting strength of, pulling strength of silver ions, and the and the fighting strength of copper metal. And so copper metal is resisting. And so maybe the silver ions are pulling with 0.5 volts, and the copper is resisting by 0.04 volts, and the net is 0.46 volts. Or maybe, we don't know actually what it is. In other words, when we look at this voltage, the voltage we call the cell potential. Equals the voltage, which is equal to V or E. E stands for electromotive force, which is voltage. And so when we look at E of the cell, in fact, we're going to use E for electromotive force. E of the cell, under standard conditions, is E naught of the anode, that is the potential for the anode, plus the potential for the cathode. Anodes where oxidation occurs, and so this is equal to the oxidation potential plus the reduction potential at the cathode. So if this is equal to 0.46 volts, this is under standard conditions. This might not be under standard conditions because we aren't given the concentrations here. But let's say this is 0.46 volts. How much is due to this term and how much is due to this term? So we have two unknowns. We have two unknowns, but we only have one equation. So if we have two unknowns in one equation, there are two things we can do. One, we could just give up and say we can't solve it because if we have two unknowns, we need two equations, right? The other way we could do this is not give up. In fact, what we'll do is this. We'll recognize that you can't have oxidation without reduction, and you can't have reduction without oxidation. You have to have both these processes occur. And so what we'll do is we'll arbitrarily assign one of these 0. If we arbitrarily assign one of these 0, then all the oxidation potentials are all screwed up. But they're all screwed up one way. They're all screwed up the same way. And all the reduction potentials are screwed up in the opposite way. So one of these is going to be too low, the other is going to be too high. But when you add them together, if one's too high, the other's too low, you add them together, those cancel out, and you get the correct answer. And so when we have two equations and two unknowns, there are two ways to handle it. One, you could just give up because we need a second equation. Or two, you can arbitrarily assign one of these 0. So which one do you want to assign 0? Should we assign the copper? Or should we assign silver ion 0? The copper, but we've already arbitrarily assigned something 0. What did we arbitrarily assign 0 before? Do you know what we arbitrarily assigned 0 before? 0 entropy, 0 delta H of formation, just arbitrarily called it 0. It was from Appendix D. Do you recall what the arbitrary 0 was in Appendix D? It was hydrogen. To do with hydrogen and H plus. So this is what we're going to arbitrarily assign 0. We're not going to assign copper or zinc or silver or whatever. We're going to assign hydrogen. Okay, this is going to be the hydrogen. We're going to call this the anode. Now, zinc zinc is a very common anode. We see zinc being used as an anode for lots of batteries. And the reason is one, zinc is easy to oxidize. So it's easy to generate electrons. And two, zinc is a good conductor of those electrons. And three, it's cheap. Hydrogen, though, hydrogen is a good reducing agent. It loses its electrons easily, but hydrogen doesn't conduct electrons very well. And so what we have to do is we have to use an inert electrode here. And so if we use an inert electrode, probably the most common inert electrode we'll use is platinum. So what we're going to have is we're going to have platinum solid, and then we're going to have hydrogen gas. Now, if this is standard, then we need the hydrogen gas at a pressure of 1 bar. That would be standard. And then that hydrogen gas, when it's oxidized, is going to produce H+. And this will be aqueous of 1 molar. And so this would be the anode, the SHE anode. And so the SHE anode is, we'll have a chunk of platinum in here. Platinum is to feed the electrons to the cathode, which would be to the cathode this way. The cathode is going to have some oxidizer in here. And so this oxidizer is pulling on the electrons. And it's not going to be successful in taking the electrons. Over here, this will be platinum 2, let's say, or some other inert electrode, or other inert electrode. So the oxidizer tries to oxidize platinum, no. Oxidizer tries to oxidize the copper, no. Oxidizer tries to oxidize the platinum, no. But if we're bubbling hydrogen gas in here, and so we'll take H2 gas at 1 bar, and we bubble hydrogen gas, the hydrogen gas is going to come into contact with the platinum. As soon as the hydrogen touches the platinum, then the oxidizer over here is successful in pulling the electrons over. And so over here at this electrode, we're going to have hydrogen gas goes to 2H plus 2 electrons. And so the potential for this is what we call the anode potential under standard conditions. And the anode potential is the potential for hydrogen gas going to H+, aqueous. And since we don't know that number, we're just going to arbitrarily call this 0 volts. And therefore, all the cell potential is due to the oxidizer. And so the cell potential here is just equal to the reduction potential of the oxidizer. And so let's take a look at that here. So in this case, the oxidizer is copper 2. So the copper 2 is trying to oxidize copper metal. It's not going to be successful. You're going to try to oxidize copper wire. It's not going to be successful. It's going to try to oxidize platinum. Not successful. But as soon as the hydrogen bubble hits platinum, then it's successful. It's going to oxidize the hydrogen gas to create H+ and electrons, and those electrons are going to be fed to the copper 2. Here, in lieu of a salt bridge, they put a porous plug here. So the cations can migrate one way and the anions can migrate the other way in this porous plug. Instead of a salt bridge. So the cell potential here is 0.34 volts. And the cell potential here is like this. It's just equal to the anode potential plus the cathode potential. If we call the anode potential 0, then that's it. And therefore, when I look at this cell here, the cell potential for this under standard conditions is going to equal E naught. This is going to be the oxidation potential here for H2 goes to H plus, and that is defined as 0 volts, plus the reduction potential for copper 2 goes to copper metal. And so this is going to equal 0.340 volts. So all the oxidation potentials are going to be all screwed up because, this is not really 0 volts. And all the reduction potentials are going to be all screwed up because this is not really 0.340 volts. But when you add the two together, then one error cancels out the other error, and then this is accurate. Okay, then we do this. The SHE can also be the cathode if H plus is a stronger oxidizer. In this case, H plus is a stronger oxidizer than Zn2 plus. And so the SHE can be the cathode, and this is written backwards because normally we write the cathode on the right, the anode on the left. It goes alphabetical, anode, cathode. If we screw it up and we write the cathode on the left, then the electrons want to travel backwards. If the electrons travel backwards and you hook up the voltmeter like you do normally, you're going to get a negative voltage because the electrons are going backwards. Does that make sense? And so what we're going to do here is this. The same thing, we're going to just measure. If the SHE is the cathode, then this is still 0 volts. Defined as 0 volts. And so here, this was the other branch. This is going to be the cathode. And E naught of the reduction potential, which is going to be equal to E naught of H plus goes to H2, is going to be defined as 0 volts. And therefore, this cell potential here is just going to be due to the zinc. And so the zinc has a reduction potential of 0.763 because it should be oxidized in this case, but it's okay. And so what we're going to do is we're just going to compile a table of values here. Here's our arbitrary 0. It's H plus 2 electrons. This is going to be a reduction. Standard hydrogen electrode.
And then, so instead of trying to measure the energy of our copper zinc cell, what we're doing is making a copper and platinum for hydrogen cell and a zinc platinum hydrogen cell, and then adding them together.
Yeah, that's basically it. And so what we're going to do is we're going to do this. We're going to just measure these relative to H plus. We don't have to do that. Once we get enough, then we can measure relative to any of these. But initially, we measure relative to this. And so here, this would be cathode. H plus 2 electrons yields hydrogen. And that cathode would generate 0 volts. So if we hook up an anode to it, then the cell potential is just whatever the anode is reading. Or we could reverse this. If we reverse this reaction, we go H2 to H plus, we change the sign. So we go from 0 positive to 0 negative. So it's still 0 volts. And so whether the SHE is the anode or the cathode is defined as 0 volts. And so 0 has a specific meaning here. What 0 means here is you're equal to hydrogen, either as a reducer or an oxidizer. If you're above 0, that means you're stronger. In this case, if we're above 0 here, we're a stronger oxidizer than H plus. If we're below 0 here, it means we're a weaker oxidizer than H plus. Okay, we only have these. These are the reduction potentials. The oxidation potentials is you reverse all these reactions and then change the sign. And so what has the highest reduction potential? The highest reduction potential is at the top here. The highest reduction potential is plus 2.866 volts, and that's for fluorine. And therefore, fluorine has the highest reduction potential. It's the most likely to be reduced. In other words, it's the strongest oxidizer. The lowest reduction potential is going to be at the bottom of the chart. And so the lowest reduction potential is minus 3.05 volts. That doesn't mean it's oxidation. It's still reduction potential. Minus 3.05 means this is a very weak oxidizer. And it's 3.05 volts weaker than hydrogen ion. And 6 volts weaker than fluorine. As we're going from positive 3 to negative 3, that's 6 volts weaker. Okay, so the negative just means weaker than hydrogen. The 0 just means equivalent to hydrogen. These are the reduction potentials. The oxidation potentials, you just reverse all these reactions and then change the sign. So as far as oxidation potential, which species has the highest oxidation potential on the chart? Which species has the highest oxidation potential on the chart? Oxidation potential means we're losing electrons. So it could be fluoride. Fluoride loses electrons to form fluorine. What's its oxidation potential? Its oxidation potential is the reverse of this. If we reverse that, we change the sign. So its oxidation potential is minus 2.866 volts. Is that the highest? No. You know what has the highest oxidation potential? Lithium. Lithium metal has the highest oxidation potential because when we reverse this reaction, we go to plus 3.05 volts. So lithium has the highest oxidation potential. It's the strongest reducing agent. And fluorine has the highest reduction potential. It's the strongest oxidizing agent. And so this is plus 3 volts and fluorine's plus 3 volts. They both have the highest. Now, if we go negative, negative just means weaker than hydrogen for half potentials. And so there's a difference here. Full potentials have an absolute 0. And so full potential would be the cell potential. Whether it's under standard conditions or non-standard conditions, the cell potential has an absolute 0. And so if the cell potential is equal to 0 volts, that's what we call a dead battery. If the cell potential is greater than 0 volts, then it's still alive. And so it's a live battery. If the cell potential is less than 0 volts, then that means you have the wrong reaction. The reverse reaction is favorable. Versus reduction potentials and oxidation potentials have an arbitrary 0. So if a reduction or oxidation potential is positive, that means it's stronger than H plus or H2. If a reduction or oxidation potential is negative, that means it's weaker than H plus or H2. But it doesn't mean that the reverse reaction takes place. And so, and the reason that the cell potential, the systematic error cancels out, so we get rid of that. Arbitrary 0, and it's all relative to H2 and H plus. Relative to H plus and H2. But regardless, the higher the potential, the more driving force there is. And so it doesn't matter if it's a reduction potential or oxidation potential. The higher the number is, the stronger it is. And so this is why lithium metal is plus 3. This is a strong reducing agent. And fluorine gas is plus 3, close to it. This is a strong oxidizing agent. Now, it depends on the equation that you use. I don't like the equation in the book. This is the equation from the book. And the equation from the book is this. They take a reduction potential, copper 2 gains 2 electrons to form copper, and a reduction potential, zinc 2 gains 2 electrons to form zinc. So they're taking two reduction potentials, but what they're doing is they're subtracting them rather than adding them. What I like to do is I just like to add the correct potentials. So I'd like to add the oxidation potential plus the reduction potential, because the higher these potentials, the more driving force, right? But here, what they're doing is they're trying to combine the two reduction potentials, but they're reversing one. So if they reverse this reduction potential, they're making it into an oxidation potential. So this is essentially just adding the two potentials. But it confuses things, because then students start to think, okay, the better reducing agent has the more negative value. Well, that's correct. I mean, the more negative value, it's better here because you're taking negative times a negative. But in reality, it doesn't work that way. It's the more positive. The more positive the value, the better the driving force. And that goes for both of these. And so people start to think differently in terms of reduction and oxidation potentials. And they get it mixed up. So if they see an oxidation potential that's 3 volts, they get mixed up because the table has reduction potentials. And so I would do this differently. And you don't even have to label them. I would do this like this. If we look at this cell up here, copper 2 goes to copper metal. That's at the cathode. So this is fine. That's at the cathode. I like to write the anode first. And so the anode, what's happening at the anode? Zinc. Zinc is some of the best metal for anodes. And so this is the anode. And so what is the potential, the anode potential there? So it's zinc goes to Zn2+. It's an oxidation potential. Okay, here it is. Zinc goes to Zn2+, so it's reverse. If it's reverse, we change the sign, plus 0.763. And so when I look at that, wow, that's 0.763 volts higher than H2. So this is a better reducing agent than hydrogen gas by 0.7 volts. Almost 0.8 volts. And so the higher the potential, the better. Zinc is a great reducing agent. Plus the reduction potential for copper 2 goes to copper. And so this is the cathode. And so we're looking at the reduction potential here. So copper 2 goes to copper. What is the reduction potential? It's up here, 0.340 volts. So this is plus 0.340 volts. So this has high, what we call oxidation potential. And this is a fairly high reduction potential, better than hydrogen here. And so this is going to give us 1.103 volts total. And so the higher the potentials here, the stronger the voltage here. So I prefer not to add reduction potential and reduction, or subtract reduction potentials. I just like to add the reduction of the oxidation, or oxidation reduction. I prefer oxidation first, because that's the way we do it in the cell. So the higher the voltage, the greater the driving force. So it turns out that the cell potential, the cell voltage is related to our driving force, delta G, the change in Gibbs free energy. And so delta G under standard conditions is equal to minus NFE under standard conditions. This is E of the cell. F is a constant. This is called the Faraday constant. N is the number of moles of electrons transferred in the balanced chemical equation. N is also equal to Z. And so they call it Z here. And so the higher the cell potential, the more positive this is, the more negative this term is, and the stronger the driving force for delta G is. Then we have a whole bunch. If we know this, then we can derive all the other equations that are related to this. That is, we know that delta G naught is also equal to delta H naught minus T delta S naught, which is also equal to minus RT ln of Q, or K in this case, minus RT ln of K. And so this is equal to minus RT ln of K. And so we can relate K with E naught of the cell. In fact, E naught of the cell is equal to minus RT, or actually divided by minus NF. And so that's going to just convert that to plus ln of K. What we like to do is we like to get this in terms of log base 10. And so this is going to equal 2.303 RT over NF, or ZF, times log base 10 of K, etc. And so we can do all the thermodynamic relationships with this, including this one, which is important. This one comes from electrical work, you know. The driving force is the maximum amount of electrical work we can do. And electrical work is how much force, how many electrons are pushed. F is the Faraday constant, which is 96,485 coulombs of charge per mole of electrons. That's Faraday there. Coulomb is a unit of charge. And a coulomb times a volt is a joule. So here we're going to have Coulomb times volt, which equals a joule. Coulomb times a volt equals a joule. Okay, so let's just do one more here. Delta G is equal to delta G naught plus RT ln of Q. So delta G is going to equal minus NFE of the cell under non-standard conditions, is equal to minus NFE of the cell under standard conditions, plus RT ln of Q. Then what we're going to do is divide by minus NF. So we're going to get E of the cell under non-standard conditions is equal to E of the cell under standard conditions. Sorry, is that mine? Okay. E of the cell under standard conditions minus RT over NF ln of Q. Then we're going to convert this into log base 10. So this is going to equal E naught of the cell under standard conditions minus RT, or 2.3, minus 2.303 RT over NF log base 10 of Q, or K, in this case, or Q. Just need Q. And so this is going to equal E naught of the cell. So we're going to restrict the temperature at 25 degrees C. We'll plug it in here. R we know, T we know, F we know. And so this is going to equal E naught of the cell minus 0.0592 volts over N, or Z, log base 10 of Q. This is called the Nernst equation. And the Nernst equation allows us to calculate the cell potential under non-standard conditions. And what we see is this. We see as the concentrations change, so do the cell potential. So if we start off under standard conditions here, what's going to happen is the voltage is going to decrease.
What does that say after the second to last line, it's still minus what quantity?
2.303. 2.303 is used just to convert natural log into log base 10. And so we can see the cell potential decreases. This is Nernst equation. This is Nernst here. All right, I'm going to stop here. We're going to look at the lab. Our lab is going to be fairly short today. What we're going to